What's the time? For quantities such as time, temperature, weight, or speed, we just have to specify a numerical value. Even if it's an evening stroll, our health watch can tell the distance we walked. These quantities are called scalars. Excursions can be aimless, but voyages are not. To account the distance as well as direction of motion, we need to record distance moved in the horizontal direction as well as the vertical direction. For bookkeeping, we have labeled these directions as the x-axis and the y-axis. Now we need a set of two numerical values. Quantities that need more than one numerical value for complete specifications are called vectors. You may argue, I can always draw a red arrow and measure my distance along this arrow. Then I would need only one number to describe my movement. The red arrow is certainly virtuous, as we will see later. But your argument has a flaw. The red vector is not self-contained. What if my dog decides to chase me to the park because I told him that cats run faster? In a two-dimensional Euclidean plane, the combination of the x-axis and y-axis is completely self-contained. Any vector in the plane can be fully described using just these two directions. To represent a vector, we write it as a column matrix. The rows of this matrix are the components of a vector along the x and the y-axis. To find the distance along the x-axis, we adjust our line of sight so it is parallel to the y-axis, and then measure the distance from the origin to where this line of sight intersects the x-axis. Similarly, to find the distance along the y-axis, we adjust our line of sight parallel to the x-axis and measure the distance from the origin to where it intersects the y-axis. In general, our vector u could be anything. I could take a walk in a random direction. I may scale down my walk to a smaller distance. I may have several different movements combined into one, or I may have to track multiple motions at the same time. There are infinitely many two-dimensional vectors that fill up this space. But this vector space follows a set of rules. We will go through these axioms later in the video. Our 2D Euclidean space is probably the simplest example of a vector space. It has only two dimensions and the choice of two orthogonal axes to express any vector ensures that the two components in the column vector are independent. They are like two colleagues who share the same office but never mix their work. To get a sense of how things change in higher dimension, we look at the three-dimensional Euclidean space. We have to expand our set of axes by including the third dimension. We label the third axis as the z-axis. As we can't show a three-dimensional object in a two-dimensional screen, we point the third axis at an angle to create the illusion of the third dimension. In this space, we have two-dimensional planes formed by the three pairs of axes, the x and the y-axis, the y and the z-axis, and the z and the x-axis. The animation in this slide shows a vector that is changing direction with time, and the corresponding change in its components along the three axes. Each projection is color-coded. When an axis is closest to a vector, it makes the largest contribution to the vector. To represent the vector u in three dimensions, We first increase the number of rows in our column representation. Just like in the two-dimensional case, the three components of the vectors are placed in 3 rows, with each component representing displacement along one axis. To obtain the components along the x-axis, for example, we set all other entries in the column to 0, leaving only u subscript x. In 3D Euclidean space, vector u also has projections along the planes defined by each pair of axes. These projections are shown by combining color pairs. Projecting onto a plane just means keeping the components in that plane and making the one perpendicular 0. So on the xy plane, we keep x and y and set z to 0. On the yz plane, we keep y and z and set x to 0, and so on. The process of increasing the magnitude of a vector without changing its direction is called scaling. When we multiply each entry in the column representation of a vector by the same number, its direction remains unchanged, but its length varies in proportion to that number. This animation shows that effect. The vector is scaled from 1 to 1.5 times its original length over a duration of 15 seconds. Multiplying a vector by a negative scaling factor reverses the direction of the vector, while changing its magnitude by a factor s. In other words, the inverted vector points exactly opposite to the original vector. Here we change the scaling from 0 to 1 for the animation on the left, but we change it from 0 to -1 for the animation on the right. The last missing piece is the addition of vectors. We revisit our previous example and modify the motion such that it is now composed of 2 parts. In the first part, the motion is entirely along the x-axis. This is shown by the vector u. The second part of the motion is shown by the vector v. It has components in the horizontal direction as well as in the vertical direction. It is straightforward to see that vector w, which is a sum of vector u and vector v, can be obtained by separately summing up components of the two vectors. We are basically adding the net movement in the x and the y direction. On close observation, we would notice that the sum of vector u and vector v can be obtained by placing the two vectors such that the head of the vector u touches the tail of the vector v. Resultant sum starts at the tail of vector u and ends at the head of vector v. Although we used our very convenient set of orthogonal axes previously, we can appreciate that the addition of vectors does not require a coordinate system. This rule works only for linear transformations, which keeps vectors straight and proportional. It breaks down for curvilinear or more generally non-linear transformations where the vector space can bend or distort. Another important point is that vectors are free to move around. By definition, they start at the origin, but for visualization, we can place them anywhere in the space without changing their meaning. In fact, we can use any two vectors to describe our motion. In this example, we are applying a time-dependent scaling to vectors u and v, the sum of which is the time-dependent vector w. We will see how this works out numerically in future videos. We are now ready to go over the axioms that define a vector space and make it a self-contained system. where all vectors operations behave consistently, making it an effective tool to solve problems in physics, engineering, and mathematics. The first rule is closure under addition. If you add any two vectors in the space, the result is still a vector in the same space. No matter which two vectors you pick, this sum stays inside the space. Commutativity of addition. Let's look at vectors u and v. First, we add v to u by placing the tail of v at the head of u. Now we switch the order and add u to v. The final vectors are identical. The order of adding vectors doesn't matter. Associativity of addition. Here are three vectors. We first add the first two, then the third. Next we add the last two, then the first one. The final vectors are identical. Grouping vectors in addition doesn't change the result. Existence of a zero vector. There's a special vector called the zero vector. When you add it to any vector, the original vector doesn't change. It acts like a do-nothing vector for addition. Existence of additive inverse. Every vector has another vector pointing in the opposite direction. It's additive inverse. When we add them head to tail, the tip ends up at the origin. Every vector has something we can add to get zero. Closure under scalar multiplication. If you multiply any vector by a number, the result is still a vector in the same space. The space is closed under scaling. Any scale vector stays inside the space. Distributivity of scalar multiplication over vector addition. Here we add two vectors first, then multiply the result by a number. Next, we multiply each vector by the same number first, then add them. The final vectors are identical. Scaling a sum is the same as adding the scaled vectors. Distributivity of scalar multiplication over scalar addition. If you add two numbers first, then multiply a vector by that sum, is the same as multiplying the vector by each number separately and then adding the results. Scaling distributes over adding numbers. Associativity of scalar multiplication. If you scale a vector by one number, then by another, is the same as multiplying the two numbers first and then scaling one. The order of combining scalars doesn't matter. Identity element of scalar multiplication. Multiplying a vector by 1 leaves it unchanged. The number 1 acts like an identity for scaling. It doesn't change the vector. In this example, we show that vectors are not limited to arrows. Here is the first monotone sound, a pure tone of a specific frequency. You can think of this tone as a vector, not an arrow in space, but a function in a function space, where the direction corresponds to the waveform shaped by its frequency, and the length corresponds to its amplitude. Now listen as we add a second monotone, another pure tone of a different frequency. The two sounds combine to form a new sound, just like adding two vectors produces a new vector. This shows that vectors are not limited to arrows in 2D or 3D. Any object that can be scaled and combined, whether a waveform, a polynomial, or a signal, can be treated as a vector. This particular example focuses on a space which we know as the Fourier space. In the next video, we will go over vector subspaces. Linear algebra was developed over the 19th and the early 20th centuries through the contributions of several key mathematicians. Carl Friedrich Gauss laid important foundations by developing methods to solve systems of linear equations efficiently and by formalizing the method of least squares, as well as studying quadratic forms which helped link algebraic structures to geometry. Hermann Grassmann then pioneered the abstraction of geometry into algebra, introducing concepts like linear combinations, independence, and dimension, effectively laying the foundation of vector spaces. Arthur Cayley and James Joseph Sylvester formalized matrices and linear transformations, creating a symbolic framework to represent and manipulate geometric and algebraic objects. Later, with the study of function spaces, mathematicians like David Hilbert introduced inner products, orthogonality, and orthonormal bases, making it possible to decompose even infinitely complex spaces into independent manageable components, and connecting linear algebra to physics, analysis, and applied mathematics. Together, these contributions transformed linear algebra from a computational tool into a powerful abstract framework linking algebra, geometry, and physics.